Welcome to MS 100 lessons, and in this lesson I will be looking at graphical analysis for F net equals to ma, which is Newton's second law. So looking at the outcomes for this lesson, I will be looking at the relationship between the acceleration and the net force, and the relationship between the acceleration and the mass of an object. And then for learning outcome number 2, I will be using a graphical analysis using a linear function y equals to mx plus c to analyze the relationship between the above variables. So according to Newton's second law, from the stating, it states that the acceleration that is induced in the object, or the acceleration that the object experiences due to a net force, is directly proportional to the net force that is applied on the object, and it is inversely proportional to the mass of the object. Okay, so when a net force is applied, the object will accelerate, and it will accelerate in the direction of the net force, and the magnitude of that acceleration is directly proportional to the net force and inversely proportional to the mass of the object, right? So that is the first outcome, which is the relationship between the acceleration and the net force, the relationship between the acceleration and the mass of the object. Acceleration is directly proportional to the net force, and it is inversely proportional to the mass of the object, right? So looking at the graphical analysis for this formula, let's say we want to perform an experiment, right? And in that experiment, we want to check the first relationship, which is the relationship between acceleration and the net force, right? So let's say we perform an experiment, and in this experiment we are changing the net force which we apply on an object, right? So the mass of the object is constant, and what we are changing is the net force which is applied on that object. And when we change the net force, we measure the acceleration of that object, acceleration in meters per second squared. Okay, so let's say we apply a net force. Let's start from 0. If there is no net force applied, right, then this implies that there is no acceleration of that object, right? So that object will remain at rest, or that object will continue to move with a constant velocity in a straight line if the net force is equal to 0. But if we apply a net force of 2 newtons, for example, since the two are directly proportional, we expect that the acceleration also increases, right? So let's say if we apply a net force of 2 newtons, we obtain an acceleration of 1 meter per second squared. And then we increase the net force to 4 newtons, and then we obtain that the acceleration now is 2 meters per second squared. And we continue to increase the net force to 6, and we obtain that the acceleration is 3, right? From this table, we can see that when we increase the net force, right, the acceleration also increases. So there is a direct proportion between these two variables, right? So now, since this is an experiment, we should have the independent variable, and the independent variable is the variable that we are changing ourselves, right? So in this case, we are changing the net force. So it means the net force is our independent variable, right? And whatever depends on the independent variable, whatever we are changing the net force, and the acceleration will change due to the change in that net force, right? So it means the acceleration is the dependent variable, right? and the variable that is constant, that is not changing, is the mass. So that is the constant variable or the controlled variable, right? The independent variable is what we are changing. We are changing the net force, and we are measuring the acceleration. The acceleration is changing due to a change in the net force, right? And from the table, we can see that when we increase the net force, the acceleration also increases, right? So from this table, we can conclude that the net force is directly proportional to the acceleration, or the acceleration is directly proportional to the net force which is being applied, right? So now, if we can represent this on a graph, to say we have a graph of acceleration versus net force. Since the net force is the independent variable, it will be on the x-axis, and acceleration being the dependent variable, it will be on the y-axis, right? So this is the acceleration versus net force. Okay, so if we were to plot the points, we'd use maybe a scale of 2 on the x-axis, 0, 2, 4, 6, 8, 10, and we'd use a scale of 1 on the y-axis, which is 1, 2, 3, 4, 5, 6, and it continues, right? So now, if we were to plot this graph, the coordinates would be 0 and 0, so that is the point. 2 and 1, so that would be 2, and then 1 there, and then 4 and 2, 4 and 2, and then 6 and 3, 6 and 3, right? So if we join all those points, we get a linear function. And we can see that the acceleration is directly proportional to the net force. When the net force increases, the acceleration is also increasing. Okay, so now we have two variables which are appearing on this graph. First, we have the acceleration, and second, we have the net force, right? So the last variable that is not appearing on this graph is the mass of the object. And remember, we're saying the mass of the object is the controlled variable, which is a constant, right? So with our graph analysis, we are trying to obtain the mass of the object from this graphical plot. So how do we perform our graphical analysis? So step number 1, we have few steps that we have to follow. And step number 1, you have to identify what type of a graph you are dealing with. And in this case, it is a linear graph, right? And that linear graph is y equals to mx plus c, right? And then step number 2, you have to substitute whatever variables you have on your graph on this y equals to mx plus c, right? Like for example, in the y-axis, we have acceleration. So instead of y, we substitute that with acceleration, right? And on the x-axis, we have our net force, right? So instead of the net force, we substitute that. Instead of using x, we substitute that with the net force. Okay, and then as you can see that the y-intercept of the graph, which is the value of c, is 0, then it means instead of c, we substitute that with 0. So that is step number 2. You substitute whatever variables you have on your graph on y equals to mx plus c, right? Okay, and then step 3, you manipulate your original formula. So your original formula in this case is f net equals to MA. So you manipulate this formula in such a way that it looks the same as the formula in step number 2, right? And then the last step, you compare. Step number 3, you compare the 3. So step 4, you compare to evaluate what each variable represents. Okay, so let us do the graphical analysis for this one. We can see step number 1, you identify the type of graph, right? We can see that this is a linear function and it is a straight line. Therefore, step number 1, we have y is equal to mx plus c, right? So that is step number 1. Okay, and then step number 2, you substitute your variables from the graph. So instead of y, we will substitute y with acceleration. Okay, instead of y, we substitute y with acceleration, and that the m is the gradient, right? So let me use mg to show that this is the gradient, not the mass, right? So this m is m for the gradient. Okay, so instead of x, what do we have on the x-axis? We have the net force. So instead of x, I will use F net, right? And what is the y-intercept? The y-intercept is 0. So it means instead of c, I'll substitute 0. So for step number 2, this is what I'm obtaining. Acceleration is equal to the gradient multiplied by the net force. Okay? And in step number 3, I manipulate the original formula in such a way that it looks like the formula in step number 2. So what is my original formula? So looking at the original formula, I have F net equals to MA, and I have to manipulate this in such a way that it looks like that. So with this formula above here for step number 2, we have A as our subject of the formula. So we have to manipulate the original formula in such a way that A is the subject of the formula, right? Okay, so let us make A the subject of the formula. We divide by the mass of the object, divide by the mass of the object. Now acceleration is equal to F net divided by the mass of the object. And remember, we are trying to manipulate this formula in such a way that it looks like the formula in step 2. Then that would be acceleration is equal to 1 over mass multiplied by the net force, right? So this is the same as that. So if I say 1 over m multiplied by net force, that would be F net multiplied by 1, and that would be F net over m. So it's one and the same thing, right? So I have manipulated the original formula in such a way that it looks like the formula in step number 2. So step number 4, we compare the two, step 2 and step 3. So in step 2, we have obtained acceleration is equal to the gradient times the net force, right? But in step number 3, we have obtained acceleration is equal to 1 over mass times the net force. So now let's compare. We can see that we have acceleration as the subject of the formula. We have net force at the end, and here in between we can see that we have the gradient being equal to 1 over mass of the object. So from our graphical analysis, we can see that the gradient, which is mg, is equal to 1 over mass of the object. So if I can write this in words, it says the gradient of that graph is equal to 1 over mass of the object. So how can we obtain the mass of the object from this graphical analysis? It means we have to find our gradient first, and then after calculating the gradient, we say that gradient is equal to 1 over mass, then we solve for our mass, right? For example, in this scenario whereby we have this table and this graph, we just have to calculate the gradient of this graph in order for us to calculate the mass, and that gradient would be equal to 1 over mass of that object, then we can calculate the mass of that object. All right, so let us calculate the mass of the object that was used for this experiment, because remember we said we are using an object of mass m, and the mass is not changing, which means that is the controlled variable, and we have our independent variable, what we are changing, which is the net force, and the dependent variable, which is changing due to the change in the independent variable, which is the acceleration, right? And then we have plotted our graph, and we found that it is a linear function, and if it is a linear function, we can perform our graphical analysis. And from our graphical analysis, we can see that the gradient is equal to 1 over mass. So we have to find the gradient of this straight line. So how do we find the gradient of this straight line? We have to pick 2 points on the graph, right? We can choose this point, which is 2 to 1 and 4 to 2, right? So 2 points, we have 2 to 1 and 4 to 2. Let us calculate the gradient. Okay, the gradient of this graph is change in y over change in x. Okay, but change in y, the y values, I mean the y-axis, we have acceleration, so that would be change in acceleration over change in the net force, right? So that is my gradient. So the gradient is equal to final acceleration minus initial acceleration divided by final net force minus initial net force, right? And we'll use these points to calculate the gradient. So that would be final acceleration, that would be 2, initial acceleration, that would be 1, divided by 4 minus 2, right? And the acceleration that we are obtaining is 1 over 2, right? So that is our acceleration. I mean, that is our gradient. So the gradient, remember the gradient is equal to 1 over mass of the object. That is from our graphical analysis up here, right? So wherever we see the gradient, we substitute 1 over 2, right? So that would be 1 over 2, which is the gradient, and that is 1 over mass of the object, right? And then now we can cross multiply for us to solve for the mass. So that would be 1 times m and 1 times 2, right? And the mass is equal to 2 kg. So it means the mass of the object that we were using for this experiment is 2 kg. And how did we obtain that? By performing the graphical analysis first for this straight line, and then we compare. For step number 1 in our graphical analysis, we see that it is a linear function, which is y equals to mx plus c. And step number 2, we substitute the variables from the graph into y equals to mx plus c. Then we manipulate the original formula in such a way that it looks like the formula in step number 2. Okay, and then our conclusion was that the gradient is equal to the inverse of the mass, or the gradient is equal to 1 over mass. And then we calculate our gradient from the graph, and then after calculating the gradient, we substitute wherever we have our gradient, then we calculate our mass, right? But according to Newton's second law, we can conclude that in this graph, we can see that the acceleration is directly proportional to the net force.